When we analyze a stream flow record, we may face a fundamental question. What type of flow regime does the catchment have? Is it groundwater dominated or surface water dominated? Is it rainfall driven or snowmelt driven? Is the river perennial, intermittent or ephemeral? To answer these questions, we have regime-based hydrological signatures. In this episode, we will look at 4 different indicators that help us characterize and classify the hydrological regime of a catchment. Stay with me. Regime-based hydrological signatures focus on the characteristic pattern and structure of stream flow. They capture features such as the overall distribution of flows, seasonal patterns, the contribution of groundwater, recession behavior, and whether the channel maintains flow throughout the year. The first indicator is flow duration curve or FDC. It ranks all the stream flow values from the highest to the lowest and shows the percentage of the time that each flow is equaled or exceeded. For this, we use a plotting position formula such as this, where m is the rank of an observation and n is the total number of observations. Besides focusing on individual points such as Q5, Q50 or Q95, we are also interested in the shape of the entire curve as the descriptor of the catchment's flow regime. Typically, the FDC can be standardized, for example, by mean or median flow, so that catchments of different sizes and climates can be compared. A steeply declining FDC generally indicates a flashy, storage-poor regime, whereas a relatively flat curve can indicate a more buffered, groundwater-dominated regime. If the curve reaches 0 at some exceedance probability, this can indicate an intermittent or ephemeral regime. One of the major strengths of using the whole FDC is that it incorporates the complete flow distribution rather than relying on a single percentile. However, there are also limitations. The choice of a standardization affects the comparison, and the extreme ends of the FDC can be poorly estimated when the available record is short. More importantly, the FDC removes the temporal information from the record. It tells us how frequently different flows occur, but not when they occur. Therefore, it should be complemented by seasonal regime indicators. The second indicator is Baseflow Index or BFI. It represents the proportion of a stream flow that is attributed to base flow over a specific period of time. This makes BFI particularly useful for distinguishing between groundwater-dominated and surface water-dominated catchments. A high BFI generally indicates a greater contribution from slow subsurface pathways, often associated with permeable geology and productive aquifers. Conversely, a low BFI is generally associated with catchments where quick surface runoff contributes more strongly to stream flow. One of the major strengths of BFI is its relatively simple physical interpretation and its strong relationship with catchment geology and aquifer characteristics. However, there is an important limitation. Base flow is not directly measured. It has to be separated from the total hydrograph, and different base flow separation methods can produce materially different BFI values for the same stream flow record. BFI can also be affected by human activities such as groundwater abstraction, surface water abstraction, and effluent discharge. The third indicator is seasonal regime coefficient, commonly known as Pardé Coefficient. This indicator describes how the mean stream flow varies throughout the year. For each calendar month, the mean monthly flow is expressed relatively to the long-term mean annual flow. When these 12 coefficients are plotted together, they produce a regime curve, essentially a dimensionless annual fingerprint of the catchment seasonal flow behavior. The shape of this curve can reveal the dominant source of runoff. For example, a single spring early summer peak can indicate a nival regime where snowmelt is an important driver. In contrast, in a rainfall-dominant or pluvial regime, peak timing follows the seasonal rainfall cycles. And finally, catchments influenced by both rainfall and snowmelt can exhibit mixed nival pluvial or pluvial nival regimes. The major strength of this curve is its simplicity and physical interpretability. It is also dimensionless, making comparisons between catchments straightforward. It is particularly useful for identifying seasonal shifts, including changes in snowmelt timing associated with climate change. There is also a limitation. Classification into simple, mixed, or complex regimes, or nival versus pluvial, is partly qualitative. Catchments don't always fit neatly into one category, and different analysts may classify borderline cases differently. The fourth indicator is flow permanence, quantified as the fraction of days in the flow record with zero values, often expressed as a percentage. This provides a basis for distinguishing between perennial, intermittent, and ephemeral streams. The major advantage of this indicator is its simple concept and the fact that it is directly observable from a streamflow record. It also has important ecological and regulatory applications. But determining true zero flow is not always straightforward. Low flow measurements are generally more uncertain, and the recorded zero may represent either genuine cessation of flow or limitations in measurement. Another issue is that a single long-term value can hide changes over time. Regime-based signatures have several important applications in hydrological modeling. Let's go through them. First, catchment classification and regionalization. Second, model structure selection. Regime signatures can help determine what processes a rainfall runoff model needs to represent. Third, environmental flow assessment and stream classification. Fourth, assessing groundwater-surface water interaction. BFI can provide valuable information about groundwater contributions, aquifer behavior, and catchment storage. And finally, identifying regime shifts due to factors such as climate change, land use change, abstraction, or flow regulation. As we saw, regime-based hydrological signatures provide a different perspective on catchment behavior. They help us identify the type and structure of its flow regime. In the next episode of this series, we will move to another family of hydrological signatures known as peak flow signatures, where we will focus on the magnitude and characteristics of high flow events and floods. Stay tuned.